So the way that I got you guys able to see my screen here is I added it. So the way that I got you guys able to see my screen here. Here's I added it.
Nice. Nice, nice, nice. Uh,
So the way that I got you guys able to see my screen.
Apache Spark, an open source data analytics engine that can process massive streams of data from multiple sources like an octopus juggling chainsaws. It was created in 2009 by Mate Zaharia at UC Berkeley's AMP Lab. Around this time, the amount of data being collected on the internet was exploding from megabytes to petabytes, making it impossible to analyze on a single machine. But there was already a clever programming model called MapReduce. You map data into key value pairs, shuffle and sort them into groups by key, then reduce each group to compute a final result. This allowed large datasets to be distributed across multiple machines, but there was still a huge bottleneck caused by disk I/O. Apache Spark fixed this by doing most of its work in memory instead of reading from disk, which can be up to 100 times faster. And that's a game changer for big data analytics and machine learning. It's used by Amazon to analyze e-commerce data, by NASA's Jet Propulsion Propulsion Lab to analyze deep space, along with 80% of Fortune 500 companies to process all their data. Despite its reputation for distributed big data processing, you can easily run Apache Spark locally on your own machine. It's written in Java and runs on the JVM, but its APIs can be used with wrappers for Python, SQL, and many other languages. To get started, install it, then let's imagine we initialize a session, and then load the data into memory. Spark will take the spreadsheet and create a data frame, which turns the columns and rows into a collection of objects between the tropics. The first step is to initialize a session, and then load the data into memory. Spark will take the spreadsheet and create a data frame, which turns the columns and rows into a collection of objects that can be processed at calls. Like in this case, we want to filter the data frame to exclude cities outside of the tropics. That transformation will have large data sets. It Spark's data number. Let's build a predictive model by first bringing in vector assembler to merge multiple columns into a vector column. Then we can split it up into training and testing data frames. From there, Spark has a wide variety of different algorithms to handle classification, regression, clustering, and so on, all of which can be trained in a distributed system. Congratulations.
MapReduce program work in two phases, namely map and reduce. Map does deal with splitting and mapping of data, while reduce does shuffle and reduce the data. So the map function will transform the data into key value pairs, and these key value pairs live here in the intermediary step of the MapReduce job or process. And then these key value pairs are shuffled around and reorganized in a way that makes sense. In the final step, they are then reduced into some final output. The output may be some file that can be used somewhere else in the system. Now, before diving deep, let's familiarize ourselves with why it was needed in the first place. Back in early 2000, Google algorithms and applications were collecting data 24/7 about people, processes, systems, and organizations, resulting in huge volumes of data. And since vertical scaling is limited, to process these large data sets, they had to horizontally scale to hundreds, if not thousands of machines. Now, when it comes to data processing data across so many machines is a very difficult task, because you need to do parallel processing across all these machines, and you have to handle failures like network partitions or machine failures. The challenge Google faced was how to process this massive amount of data with speed and efficiency and without sacrificing the meaningful insights. This is where the MapReduce programming model comes into rescue. Back in 2004, two Google engineers wrote a white paper on MapReduce model, which allowed engineers to process very large data sets that were spread across hundreds or thousands of machines in a distributed setting very efficiently in a fault-tolerant manner. It's a pretty short white paper, but maybe fairly complex to understand for some. But I highly encourage you to skim through that. You can find the link in the white paper in my description. In this video, I will give a high-level understanding of MapReduce framework with examples in the context of system design interviews. Now, if you have a Python or JavaScript background, you are certainly familiar with MapReduce functions. Here in the context of MapReduce in distributed system settings, map and reduce are a little bit different. Google engineers realized that most of the data processing tasks could be split up into two steps, and they created a library that allowed engineers to process huge data sets in order of terabytes spread across thousands of machines. And this is a fairly simple concept to understand. There is this map function that transforms the data into key value pairs. The key value pairs are shuffled around and reorganized. They are then reduced to some final output. Now, before understanding it any further through an example, there are a few things worth noting. The first thing is that when dealing with MapReduce model, we assume that we have a distributed file system, which means we have got some large data sets that are split up into chunks. These chunks are replicated and spread out across hundreds of thousands of machines. And then this distributed file system has some sort of central controller which is aware of everything going on in the MapReduce job. Meaning the central controller will know where exactly the chunks of data resides and is able to communicate with all the machines that store or processes data. That is the map machines or reduce machines or locals. The second thing to note is that since we are dealing with very large data sets, we don't actually want to move these large data sets. We let them live where they currently live on their respective machines. What we do is we have these map functions operate to the data locally. So instead of grabbing and aggregating the data and move it somewhere else, we instead send the map programs to the data and avoid moving all this large data. The third very important thing to note about this model is the key value structure of data in the intermediary step is very important, because when you perform a reduce or reduce data chunks, these data chunks come from the same data set. Because remember, all these data chunks are the chunks of the same large data set. So when you reduce these data chunks, you're likely looking into some sort of commonality or pattern in these various pieces of data. Because when you've got key value pairs, you'll have some keys that are common, some keys that are common up here, some keys that are common up here or down here, and it becomes easy to reduce that into one single meaningful value based on that key. This will become very clear when we deep dive into our that commonality or pattern in these various pieces of these data chunks. You're likely looking into some sort of commonality or pattern in these various pieces of data. Because when you've got key value pairs, you'll have some keys that are common, some keys that are common up here, some keys that are common up here or down here, and it becomes easy to reduce that into one single meaningful value based on that key. This will become very clear when we deep dive into our example. The fourth thing to note is how the model handles machine failures or network partition. To handle failures, the MapReduce model basically reperforms the map operations or the reduce operations when the failure occurs. So if a failure occurs in the step here, that is maybe there was a network partition when generating the key value pair. The central controller, which I mentioned earlier, will just reperform this operation and then move on to the reduce step. Reverse the operations when the failure occurs. So if a failure occurs in the step here, that is maybe there was a network partition when generating the key value pair. The central controller, which I mentioned earlier, will just reperform this operation and then move on to the reduce step. And this can happen only if the map and reduce functions are idempotent. That is, if you repeat the map or reduce function multiple times, the output doesn't change. The outcome doesn't change regardless of how many times you repeat the map or reduce function. So, idempotency is a requirement in the map reduce model. Now, when engineers are dealing with the map reduce model, they just need to make sure that they have a good understanding of the inputs and expected output. That is, what is the output of the map function, what is the intermediary key value pairs look like, how they can be reorganized in a meaningful way, which as an input to the reduce function, and allow it to optimally reduce to a final output. As you can see, this framework simplifies a lot of things for engineers. Engineers just need to worry about the input and output data in various steps. They don't need to worry about the intricacies and complexities of processing large data sets in a distributed system. Basically, engineers will end up using some sort of library implementation, such as Hadoop, and they just need to be aware of the various inputs and outputs of these various functions. Alright, with all these points in mind, let's understand it through an example, which I am taking from the same white paper presented by the Google engineers. So here I have a set of input files, and typically these input files will be distributed across several machines. For our example, for the sake of simplicity, I just have 2 input files, and our task here is to count the number of occurrences of each unique word across all the files. So here, our first file contains the sentence, "This is an apple," and our second file contains, "Apple is red in color." The mapper here counts the number of times each word occurs from the input splits in the form of key value pairs, where the key will be the word and the value is the frequency of the word. So the word "this" occurs 1 time, the word "is" occurs 1 time, the word "and" occurs 1 time, and the word "apple" occurs 1 time. And same with the other input file, where it says "apple is red in color." The word "apple" occurs 1 time, "is" occurs 1 time, "red" occurs 1 time, "in" occurs 1 time, and "color" occurs 1 time. By the way, both these operations, both the mapping operations are happening here in parallel. Now, once the mapping is done, it is followed by a shuffle phase, which is a lot of times ignored during the map reduce discussions, but it's a critical step. Here, we group the values by keys in the form of key value pairs. So here we got a total of 6 groups of key value pairs. And these shuffling or grouping of keys makes the job of reducer so easy and efficient. Because now the same reducer is used for the same key value pairs with the same key. Now all the words present in the data are combined into a single output in the reducer phase. And the output shows the frequency of each word. Here in the example, we get the final output of key value pairs as "this" occurred 1 time, the word "is" occurred 2 times, "and" occurred 1 times, "apple" occurred 2 times, "red" occurred 1 times, "in" occurred 1 times, and "color" occurred 1 times. The trickier part in the context of system design interviews is to be able to identify this pattern of map reduce. That is, given a problem, can you solve that problem using map reduce? Is that the real use case? So that is something you need to be able to identify, and which comes by solving more and more problems. So for example, you are given a large data set of millions of YouTube videos and their metadata information such as the likes, the comments, the engagement rate, the length of the video, and whatnot. And let's say you are asked to find all the videos which have certain number of likes. So for this, you need to pass through the entire metadata information of all these videos and then finally produce an output file. And likewise, whenever you're given a large data set where you have to deduce or analyze the large data set, where say the files are distributed across many machines and you need to analyze all the files collectively somehow, that is a key hint of applying MapReduce. With that, I hope this video made sense, and for any future system design problems, you will be able to identify whether to apply MapReduce or not. At least you should be able to have a discussion with the interviewer to check if applying MapReduce makes sense on a particular problem.
Okay. Switch to map reduce to divide. Okay.
Welcome to Bite-Size Data Science. We left off our Spark discussion talking about RDDs, data frames, data sets, driver programs, and why you may want to use Spark. In this video, we'll go a bit deeper to get an understanding of how to use Spark. In this video, we'll go a bit deeper to get an understanding of how Spark works by looking at resilient distributed datasets. Don't worry, you don't need to be a hardcore software engineer to understand this. We said that a Spark client is a driver program that talks to a Spark server. That's not really different from you using your browser to view YouTube videos like this one or to access email. By the way, I've heard many times people say that Spark is easy. Keep in mind that it is still programming. You have to learn the classes and methods and know how to use them. As we saw earlier,
You don't need to learn classes and methods now. You just need to understand the architecture. I think that will be more than enough to survive today's age. How old is this video? It came out 7 years ago. So that checks out.
an RDD is an abstraction of your distributed data. It has a few interesting features. First, it is immutable, which means that once created, it cannot be modified. This is convenient when it comes to resilience. When you execute operations that change an RDD, Spark creates a new one and keeps track of where it came from. For example, if you have your initial data in an RDD called RDD1, and you convert some
Yeah, so I just noticed that there is some issue with the audio and the OBS. Maybe there is some mirroring going on. I'll try to fix this issue. Hmm. What if I just mute this, or should I mute myself? Yeah, I should just mute this. That will be good.
If you have your initial data, when you execute operations that change an RDD, Spark creates a new one and keeps track of where it came from. It's convenient when it comes to resilience. When you execute operations that change an RDD, Spark creates a new one and keeps track of where it came from. For example, if you have your initial data in an RDD called RDD1, and you convert some fields from character strings to numbers, the new RDD, RDD2, will contain these modifications, but also remember the operation and that they operated on RDD1. So, if the creation If you have your initial data, an RDD called RDD1, and you convert some fields from character strings to numbers, the new RDD, RDD2, will contain these modifications, but also
Okay, that's
if an RDD fails for any reason, it only needs to go back to the previous RDD and start from there instead of having to go all the way back to reading the data from disk. You may say that all these copies will eat up your memory quickly. That's possible, but Spark will manage memory and remove what is not needed. For example, if you are now at RDD3, do you really need to keep RDD1 since you have RDD2? Once RDD3 is created, do you really need to keep RDD2 around? Of course, it is a bit more complex since you could create RDD4 based on RDD1, for example. We can see that we can have quite a chain of RDDs, and with many branches, it starts looking like a tree. Let's say RDD1 is used to create RDD2 that converts a character date field into a datetime type, and then you use RDD2 and convert the salary character field into a floating number to end up with RDD3. Isn't that a waste of resources to read all the records twice? Yes, it is. There is space for optimization, and Spark does it. The operations on an RDD can be transformations or actions. The creation of RDD2 and RDD3 involves transformations. Since you're not doing anything with your data, Spark knows what you want to do, but does nothing. This is called lazy evaluation. Once you decide to really do something like return the average salary of all employees by department, then Spark starts doing all the transformations that are required for the action, the averages. This way, it can look at all the transformations and decide the most efficient way to get there. Why do you need to know this? That's because many people run into problems and don't realize that it is not the last action you took that is the problem, but many transformations before it. You may think, that's simple, I get it. Still, I guarantee that many of you will run into problems because of the lazy evaluation. After you spend many hours trying to figure out why your average fails and see the error in a previous transformation, you'll get it and be fine from that point on. The concept of lazy evaluation, transformation, and action also applies to data frames and data sets, so always keep that in mind. Here are examples of transformations. For example, you could decide to extract the distinct records from a file. This is noted, and the evaluation will happen later. If you are planning to send results back to the driver program, then it is an action, and the execution must happen. When writing their code, people often add actions to their processing just to make sure the transformations are working. These extra actions can be removed once you're confident of your transformations. So, remember, Spark uses lazy evaluation, so errors can be anywhere since the last action.
Prices RDDs are called partitions and may be but do not need to be computed on different nodes of a distributed systems. Okay. So we can add this here. By the way, all the notes that I'm taking here will go through some OCR model to capture all the text that is like very gibberish looking. And then we will like create summary out of these things for recalling all the stuff that I've written later. Right. So yeah, if there are some open-ended questions like this, right? Idea is by OCRing them, uh, I'll have a better record, which I mean can be used in conjunction with any modern machine learning model. Yeah, I don't know what I said, but let's see. IDs, please are mutable. Okay. Easy evaluation. Completely delayed till necessary norms. Completely Spark does not begin computing the partition until an action is called. An action is the Spark operation that is something that the RDT triggering evaluation of a partition possibly reading some output or non-Spark system also the Spark is for example repetitive with operation the scheduler. Basically, action is a function which takes RDD as an input and produces anything that is not an RDD. Okay, understood. Which means directly setting the based on the competence and if you assume that the Spark values action by working on which will be each object in the final distributed data set. Okay, I do not understand this. Based on the dependency between arbitrary transformation and the Spark values and action by working backwards and the series each object in the final data set. Okay. Using the series itself, all the execution lines in the quotation. Not all transformation languages in this software key needs to evaluate the RTD to derive the range of data set of the transformation and action is given. Partition evaluation. So, meaning by evaluation. Right. जो ये उतना बुरा नहीं लग रहा है एक्चुअली, है ना? एक्चुअली बुरा नहीं लग रहा है। नहीं, बट खेलना हम खेलते। Spark's performance advantage over MapReduce is greatest in case involving repeated computation. Much of this performance increases due to Spark's use of in-memory persistence. Okay, rather than writing tests between each pass through the data, Spark has the option of keeping the data on the executed rules in the memory. Uh, okay, so now that we are on this topic, I think हम एक चीज कर सकते हैं. One moment, okay. Yeah. Performance bottlenecks. ये होती है ना spelling. हाँ. Okay. Yes. So now that we are on the topic of performance bottlenecks, so here they are saying, right, कि in case of using Spark, like in use cases involving repeated computation, much of this performance increase is due to Spark's use of in-memory persistence. Rather than writing to the disk between each pass through the data, Spark has the option of keeping the data on the executor stored into memory. That way, the data on each partition is available in memory each time it needs to be accessed. So, ऐसा क्यों है कि keeping the data in memory leads to higher performance? We will go through this. Okay. So, suppose that this is some mathematical operation. For example, let this be a matrix A. Okay. And there is another matrix B. This is a n by n matrix, and this is also n by n matrix, right? So, हर एक computation करने में, let's see how many operations we are doing, right? अगर मुझे एक computation करना है, तो उसके लिए I'll pick n elements. Okay, this is a cross product to produce a dn by n matrix, right? This is D. तो D का ये एक एलिमेंट करने के लिए लेट्स सी हाउ मेनी बाइट्स वी नीड टू ट्रांसफर और कंप्यूट जो भी है. तो n elements of A, n elements of B, right? अब सपोज कि each of this is a 32-bit number, right? तो बेसिकली 4 bytes, right? तो 4n तो बाइट्स आई हमारी A से, 4n बाइट्स आई हमारी B से. ये रीड ऑपरेशंस है. दीज आर जस्ट रीड ऑपरेशंस. 4n बाइट्स फ्रॉम A, 4n बाइट्स फ्रॉम B, राइट? हाँ, ओके, वेरी गुड. और फिर अब राइट ऑपरेशन देखते हैं हम लोग. राइट ऑपरेशन होगा कितना? बस 4 बाइट्स का, राइट? तो जो टोटल डेटा इन्वॉल्व है इसमें is what? 9n. We are good about this. Okay. Yeah. और हम यहाँ पे अगर कंप्यूटेशन देखेंगे ना, तो वो कितनी है? Each element of this will interact with each element of this, right? So in total there are n such multiplication going on, और उसके बाद n-1 एग्रीगेशन ऑपरेशंस. सो मतलब हमारे पास अगर एक बार मल्टीप्लिकेशन होने के बाद ये एलिमेंट वाइज आ भी गई ये सारी चीज़ें, तो हमें मुझे इसमें से इसे प्लस करना पड़ेगा, इसे इसमें प्लस करना पड़ेगा. तो 3 थे तो हमें 2 बार करना पड़ा. तो ये दैट इज 2n-1 operations, right? So if you look at it closely, we can see कि 9n bytes के read, right? 9n plus 4 bytes के read और write के लिए हमने 2n-1 operations करे, है ना? अब इन केस n बहुत ज़्यादा बड़ा हो जाता है, बहुत ज़्यादा ही बड़ा हो जाता है, right? So it becomes 2 by 9, है ना? तो इन लार्ज केसेस ऑफ n, जब ये मैट्रिक्स बहुत ही ज्यादा बड़ा हो जाएगा, तो we are achieving this kind of a efficiency. This is called arithmetic intensity. Arithmetic intensity. Number of byte, no, sorry, byte movement divided by computation on those bytes. One moment. हाँ, राइट. अब हम किसी भी अगर मॉडर्न एक्सेलरेटर को ले, राइट, तो अब हम लोग सुनते हैं ना कि ये जो जीपीयू है, this GPU has a flops of say 10 petaflops. Peta 10 चल 10 teraflops ले लेते हैं, teraflops, right? और इसमें जो मेमोरी बैंडविथ है, दिस इज 1 terabytes per second, राइट? तो इसका मतलब ये है कि अगर इसके पास 10 टेराबाइट एक सेकंड में आई, तो उस पे ये 10 टेराफ्लॉप्स के ऑपरेशन कर सकता है, राइट? तो बेसिकली फॉर एवरी सिंगल बाइट इट इज एबल टू परफॉर्म 10 operations, but this matrix multiplication that we are doing here right now, is a single operation is only able to generate a arithmetic intensity of 2 by 9, which is what, 1 by 1.45, right? Which is roughly equal to point 6.56 something, right? This is a lot less than the actual arithmetic intensity that the hardware can provide. So this is a computationally inefficient process, right? अब इन्होंने बोला कि keeping this in memory can save us, मतलब is helping the Spark architecture. So why is it the case? This is the case because कंप्यूटेशन रिमेनिंग सिमिलर, क्योंकि यहाँ पे कंप्यूटेशन तो चेंज नहीं होगा. सपोज हमें मतलब मैट्रिक्स मल्टीप्लिकेशन ही करना है स्पार्क के आर्किटेक्चर से, सो कंप्यूटेशन विल रिमेन सेम, but the thing that we can change is the way this is coming on to this computation, right? So rather than reading it from a disk which is stored far away from this compute accelerator, why don't we store it in something which is nearer to it, right? Like a RAM, which is faster also. So rather than loading things from here to here, then here to here, what they do, what Spark is doing right now is lazily, it keeps some of these values here in RAM, right? तो जैसे जैसे यहाँ पे वैल्यू चाहिए होती है, वो डायरेक्ट रैम से जाती हैं, और हाँ, फिर हम धीमे धीमे से पॉपुलेट करते हैं. तो हमने इस रास्ते को छोटा कर दिया है. तो आप जैसे अगर मेमोरी हायरार्की देखोगे, इट्स लाइक दिस कि हाँ, ये आपकी इंटर थ्रेड मेमोरी जो भी हो गई, फिर ये आपकी L1 कैश, L2 कैश, L3 कैश, फिर ये आपकी रैम हो गई, एंड देन यू हैव दिस SSD और डिस्क, right? The closer, the higher any memory is on this pyramid, the closer it is to the place where the actual computation is taking place. So by keeping more and more of my R data points on this RAM, we are able to uh, like saturate these compute nodes faster, right? There is a graph for this, which is called a roofline analysis, right? This, all this being similar, right? So this is the hardware line, you can't cross this line, right? This is the hardware limit, 10, right? It keeps growing, then it dips. If you are in this region, if you are in this region, you are memory bound. That is, you can increase the efficiency of your memory access pattern. By increasing the memory access pattern efficiency, we simply mean that you can instead of loading things from disk, maybe you can move things from there to some lower hierarchy or higher hierarchy of this pyramid, and then your memory access pattern will increase, right? This is the compute intensity, right? This is something you can't change. Uh, right? So the moment, even if after some point you're able to increase the memory bandwidth, if this computation is only this much intense, then there is no point in increasing further memory accesses, right? You can do well without this. So yeah, this is a simpler diagram to visualize all this. Okay, this something, sorry, I went off on a tangent, but I think this was important. मे बी आज यहीं तक पढ़ेंगे, इस वाले को खत्म करके विल सी सम वीडियो फंक्शन ऑफ RDDs. I yeah, you'll finish this और फिर हम बाकी बुक कल पढ़ेंगे. The tutor was
Do you know about narrow transformations and wide transformations? So these are the two sets of transformations that we have in the part. Narrow transformation are those transformations wherein the number of additions before and after the transformation remain the same after going to the transformation as well. Few examples of them like filter map. So if we have 5 partitions before this transformation, once we do it, the number of partitions remains same, which is like 5 in this case, and there is no shuffling or the exchange of data between the partitions. Whereas in case of wide transformation, what happens is we have an exchange of data among the partitions. So a few examples of this like being proved by join, and the number of wide transformations defined in those stages. They're not durable, they're not user friendly, and they're not safe. Welcome everybody. Count in size, a local count on each. Whenever you are using a new one, the original further transform to change the transform 6 kilo. So it has the
इसमें मजा आएगा. But I think Uh, okay, maybe partner. I'm just running already. So I think you know, 9%. ओके, आई थिंक अभी के लिए इतना ठीक है। बाकी या बाकी we can continue from this tomorrow. ये नहीं चल रहा है इस पे सही से। बट या आई थिंक दिस इज गुड, दिस इज गुड प्रोग्रेस फॉर द डे। और हम कल पेज नंबर 45 से कंटिन्यू कर सकते हैं, है ना? T5 number 45. Yes. Oh, number 28. Yes. Okay, और इसके बाद maybe let's watch this video.
Not just better, maybe. When you encode text into binary, it's often nice to use as little. You'll notice lots of ups, about half as many, with some notion of intelligence. We will get to modeling language, which is wonderfully complicated, but it helps to warm up with a simpler example containing the same essential ideas needed for our path of rediscovery. Imagine you have a robot that we have sent to a faraway moon whose job is to wander the surface and collect data. From here on Earth, we send it instructions for how to move that are going to be limited to 4 very simple possibilities: move up, down, left, or right, each one with a fixed step size. The nuance will be that these instructions are not uniformly distributed. Half of everything we send is up, 1/4 of the instructions are down, 1/8 are left, and the other 8 are right. It's a little contrived. It's meant to be a simple example. And in that spirit of simplicity, we're also going to assume that every instruction is independent. They are sampled from this distribution regardless of the preceding context. When we send data to the spot far away, we're doing it as a stream of bits, ones and zeros, and it's very slow and costly to do that. So the natural question, the warm-up puzzle for you today, is to ask, what is the most efficient possible way to encode these instructions as a stream of bits? And here, we might imagine 3 students who each attempt an answer, one who's straightforward, one who is clever, and one who is very theoretical. The straightforward student immediately raises their hand and says, well, for each of these 4 instructions, we could just use 2 bits. Maybe 0, 0 encodes up, 0, 1 encodes down, 1, 0 encodes left, and 1, 1 encodes right. On the receiving end, this makes it very easy for the robot to decode. It simply breaks up the bit stream into chunks of 2 and translates each chunk into the appropriate instruction. Now, the clever student points out, well, that does nothing to take advantage of the fact that up comes up way more frequently than left or right. They propose a method where we use a different number of bits for each instruction. I'll explain it in just a second, but I do want to call out the fact that as soon as you let different instructions get different numbers of bits, it's certainly not obvious that the robot is going to know how to decode it. After all, it needs to somehow know where to draw the dividing lines. Now, being very clever, the second student has thought that through, but it's easy to explain if I just kind of lay it all out. What they suggest is letting the single bit 0 represent up, letting the 2 bits 1, 0 represent down, using 1, 1, 0 for left and 1, 1, 1 for right. You can calculate the average number of bits per instruction.
और के बाद अगर 1 आ गया तो it can, अगर 1 आ गया तो it can't be the first thing. 1 के बाद अगर 1 आ गया तो it can be left or right, but 1 के बाद 0 आ गया तो we end. So okay, agreed.
Instruction that this would require with a simple weighted sum. Half the time, only 1 bit is used, a quarter of the time, 2 bits are needed, and the remaining times, you need 3 bits.
Can't we do this कि अगर 0 के बाद अगर 0 आ गया तो भी तो नहीं है कुछ?
When you add this all up as a weighted sum, you get 1.75 bits per instruction, which is indeed better than the more naive approach of a flat 2 bits per instruction. The second student is spending more bits on those last 2 instructions. Because they come up so much less frequently, this is more than made up for by using only 1 bit for that most common instruction. And you can see this efficiency bear out empirically too. This right here is a set of instructions sampled from that distribution. You'll notice lots of ups, about half as many downs, and even fewer lefts and rights. When you turn each symbol into the appropriate bit string following this encoding, the resulting sequence of bits is indeed shorter than what the naive method gave. But I hear some of you asking, how does the robot know how to decode this? Can we be sure that there's an unambiguous way to draw the dividing lines? In the lingo of encodings, each of these 4 bit strings used to encode the instructions is called a code word. And as we step through things here, see if you can figure out what rule the clever student was following to make sure that their code words don't conflict with each other. And really, you just need to look at an example bit stream from the robot's perspective and think it through. Let's say that very first bit that it receives is a 1. So far, this could be encoding any of the last 3 instructions, down, left, or right. If what follows is a 0, then it can only be down. There is no other possibility, so the robot can register that as a complete instruction. From there, starting fresh, if what follows is a 0, that must be encoding up, since there is no other possibility. Nothing else starts with a 0. After that, if they see a 1, this is so far ambiguous, it's the prefix for any of the last 3 code words. If the next bit is another 1, it remains ambiguous, it's the prefix of the last 2, but that following 0 then makes clear these 3 bits must have been encoding left. In short, all the robot has to do is read in the next sequence of bits until the moment that it forms a complete code word, at which point it can register it as a complete instruction. If you step back and think about it, the key constraint for this all to work is that no code word can be a prefix of another one. For example, let's say you tried to introduce some fifth instruction that had the code word 100. That would cause conflicts, because after reading 10, it's not clear whether that's supposed to be down or if it's supposed to be the start of this new fifth instruction. When you avoid this kind of conflict, an encoding method like this has a special name. It's known in the business as a prefix-free code, or what is confusingly synonymous, it's actually more commonly known as a prefix code. And there's a really nice way to visualize choosing prefix-free codes with a certain diagram that represents every possible binary string. This diagram also has some helpful parallels with how I want to show entropy in just a few minutes. It's probably decently intuitive what's going on if you just pause and stare at it for a bit, but I'll call out the important features. Each layer shows every bit string of a given length, and you'll notice everything that starts with a 0 lives on the left half of this diagram, and everything that starts with a 1 lives on the right half of the diagram. And that same idea continues recursively as you go up. So everything starting with 00 is above this quarter of the diagram, starting with 01 is above this quarter of the diagram, and so on. In particular, the key property is that every binary string in this diagram is a prefix for everything that sits above it. So when our clever student chose to allocate a single bit 0 to represent the instruction up, they were effectively consuming half of the space of all possible code words by doing so, since everything starting with a 0 is now prohibited based on this prefix-free property. Similarly, allocating 10 to down eats up another fourth of this space, and the remaining 2 instructions each eat up an eighth of the space. You can just see how nothing is left over. And at this point, I'm guessing that there's some bell kind of resonating in your mind, given that these proportions are all exactly the same as the probability of the space of all possible code words by doing so, since everything starting with a 0 is now prohibited based on this prefix-free property. Similarly, allocating 10 to down eats up another fourth of this space, and the remaining 2 instructions each eat up an eighth of the space. You can just see how nothing is left over. And at this point, I'm guessing that there's some bell kind of resonating in your mind, given that these proportions are all exactly the same as the probability for each instruction coming up. And in fact, that tickling sensation of a relationship between data size and probabilities is exactly the founding insight for information theory. When you stare at this pleasing alignment, it might suggest that the clever student solution is not just better, maybe it's somehow perfect. But at the moment, that feels like a bold claim to make. How could you know that there's not some ultra clever method that does something fancy with really long sequences of instructions that somehow makes the match 0 to represent the instruction up? When our clever student chose to allocate a single bit 0 to represent the instruction up, they were effectively consuming half of the space of all possible code words by doing so, since everything starting with a 0 is now prohibited based on this prefix-free property. Similarly, allocating 10 to down eats up another fourth of the space, and the remaining 2 instructions each eat up an eighth of the space. You can just see how nothing is left over. And at this point, I'm guessing that there's some bell kind of resonating in your mind, given that these proportions are all
computationally inefficient.
Exactly the same as the probability for each instruction coming up. And in fact, that tickling sensation of a relationship between data size and probabilities is exactly the founding insight for information theory. When you stare at this pleasing alignment, it might suggest that the clever student solution is not just better, maybe it's somehow perfect. But at the moment, that feels like a bold claim to make. How could you know that there's not some ultra clever method that does something fancy with really long sequences of instructions that somehow makes it so the average bits per instruction gets even lower than this? This takes us to the third student, head in the clouds, who is not really even thinking about actual codes that they can implement. They have been pondering what properties a perfect, optimally efficient code would have. They have this really clever idea, which is to argue that random noise should be incompressible, and therefore, a perfect compression algorithm should produce a bit stream that's indistinguishable from random noise. What's neat is, even though that sounds kind of simple, this can actually lead you to reinventing the idea of Shannon entropy. Now, when I say random noise, what I mean is that each bit is a 1 or a 0 with 50% probability, and all of the bits act independent from one another. It's not hard to show that our second student's encoding for the robot genuinely follows this rule. If you think about it, there's a 50% chance that the message starts with the instruction up, so that first bit has a 50% chance of being a 0, otherwise it's a 1. And then if it is a 1, there's a 50% chance that the instruction is down, meaning the next bit is 0, otherwise it's a 1. And so on. Each new bit really does act like an independent coin flip. So to the receiver, that compressed bit stream really is indistinguishable from random noise. But why am I saying that random noise is incompressible? Well, for that, let's really focus on things from the receiver's perspective. And here, instead of thinking instruction by instruction, it helps to zoom out and frame our discussion in terms of entire messages and what the encoding for full messages looks like. When that receiver sees a string of n bits representing some compressed message, this is 1 out of 2 to the n possible messages they could have received that would have the same size. And then critically, because we're assuming this looks like random noise, all 2 to the n of those messages must be equally likely. Now, to be clear, we're not just talking about the robot example anymore. Our theoretical head in the cloud student really wants to make an argument for what perfect compression looks like for any data type. Like maybe we're compressing language or compressing images, and they want an argument that works regardless of the details of what specific compression algorithm you're using. A loose intuition in your head is that maybe among all of the messages that compress down to n bits, some of them would contain a larger amount of predictable data, while others would have started as a smaller amount of unpredictable data. But the key point is that if the compressed bit stream really does look like random noise, meaning all of the bit strings of size n are equally likely, it must be the case that all the underlying messages being compressed were equally likely to arise, and even more specifically with probability 1 over 2 to the n. So again, why am I claiming that this is incompressible? Well, let's pull up that same diagram representing the space of all possible binary strings. In this case, we can think of all the encodings for our 2 to the n equally likely messages as being the bit strings on one layer of this diagram. If you tried to define an alternate scheme where you try to become more efficient by making one of these messages use fewer bits, it would move lower on the diagram, which means it then overlaps with some other message, so you would have to put that other message somewhere else in this diagram. At minimum, that means it's sharing a space with yet a third message, and those last two have to kind of get bumped up one layer, requiring that extra bit for each of them to disambiguate. So saving 1 bit over here costs you 2 bits elsewhere. You're basically pushing down a bump on the rug, only to see it pop up even worse in another spot. In general, any message encoded with a string lower on this diagram is going to be eating up more than its fair share of the space, which forces multiple other messages to occupy a smaller region, bumping them higher up, meaning they're encoded less efficiently. I'm going to guess that it's decently intuitive for everyone watching that the most efficient scheme here for equally likely messages is to give them all the same number of bits, but I do think the diagram gives a more concrete way to see why you end up with unfavorable trade-offs otherwise. Once you have this idea that perfect compression looks like random noise, this is exactly the kind of thing I was referencing in the intro about how insights can lead you to definitions. Notice how what we're basically saying is that a message that uses n bits in a perfect scheme must have a probability of 1 over 2 to the n, or 2 to the negative n. If you take the log base 2 of both sides here and then negate, this is equivalent to saying that the number of bits allocated to a message, assuming perfect compression, is negative log base 2 of p, where p is the probability of perfectly 4 bits emissions. Notice how what we're basically saying is that a message that uses n bits in a perfect scheme must have a probability of 1 over 2 to the n, or 2 to the negative n. If you take the log base 2 of both sides here and then negate, this is equivalent to saying that the number of bits allocated to a message, assuming perfect compression, is negative log base 2 of p, where p is the probability of occurring. This negative log expression is the fundamental formula for all of information theory. Everything up to this point is me trying to make this value feel like something you are inevitably drawn to by asking about perfect compression, rather than it feeling like some arbitrary definition that we start with. Some students do find this negative log takes a little getting used to. It looks like it should be a negative value before you think about the fraction in the middle. But really the intuitive way to read it is that it's asking how many times do you chop your space of possibilities in half to get to a certain quantity. Here, let me pull up some axes and show you the graph of negative log of p. I've also seen some authors default to writing this as the log of 1 over p, which maybe you find more intuitive. You could also think of it as the log base 1/2 of p, which I've never really seen anyone lean into, but personally I would be quite partial to that as a convention. Now, however you write it, what Shannon realized is that this is a very useful way to think about the information that a message contains, even when literal perfect compression is not possible, and p is no longer a clean power of 2, which would mean that the output here is some fractional amount. In fact, he defined this expression to be the information of an event. The image I sometimes have in my head is to picture the probability of an event with a little pie chart, and the information is this bar above it that gets kind of pumped up to be taller as the probability is squeezed closer to 0. That is, unlikely messages contain a lot of information. And the bar is relaxed to get shorter as the probability approaches 100%. Highly expected messages contain very low information. I want to be clear that there is content to this definition. It's more than just rescaling probabilities, as if converting to an alternate unit system. You've already seen the core idea. In a perfect compression scheme, the number of bits allocated to a full message precisely equals this information content. Now, of course, perfect compression is not always possible. Your probabilities of messages are likely not perfect powers of 2. So the more general way you would frame this is to say that the information of a message gives you a lower bound on how much it can be compressed. At least when you average overall possible messages, it's perfectly possible to overfit a compression algorithm to one specific case. And to really wrap your mind around information and fractional bits, we need to step up our game beyond that warm-up example. See, with the robot, the probabilities were overly clean. They were all perfect powers of 2, so that the information per symbol could precisely match a whole number of bits. But Shannon was very interested in this question of limits on compression for much more realistic and complicated cases, like natural language. For example, here I'll pull up the probabilities for each new letter in an example phrase, at least as determined by a little GBT that I'm running locally. And by the way, if the probabilities provided by a model feel like those might be distinct from the probabilities of actual language, you would be right to raise an eyebrow. Hold on to that thought. It becomes very relevant later. One key difference with language is how heavy locally. And by the way, if the probabilities provided by a model feel like those might be distinct from the probabilities of actual language, you would be right to raise an eyebrow. Hold on to that thought. It becomes very relevant later. One key difference with language is how heavily dependent on context everything is. The probability distribution for each new letter you see is highly contingent on everything that came before it. The other big difference is that all of these probabilities are obviously not going to be clean, perfect powers of 2. So if you compute the Shannon information of each one of these, meaning you take the negative log base 2, all the numbers that you see are fractional amounts. And again, giving a vague interpretation of what these mean is really not hard. Information content is low for very predictable letters, and it's high for very unpredictable letters. But all of you watching this are smart enough to demand a more exact interpretation, one that justifies why these values deserve to be given the units of bits. I mean, it's not like there's going to be some perfect encoding where this letter I has a code word that is somehow 4.19 bits, or where this highly predictable O is somehow encoded with just a narrow sliver of a bit. The real meaning is related to encoding entire messages and coming up with a bound on their compression. The probability for a full phrase, like the one I'm showing here, looks like multiplying the probabilities for each successive new letter. Where, again, I'll emphasize that these successive letters' probabilities are conditioned on what came before. This is essentially the chain rule from probability. I want you to notice how nicely this plays with a logarithm. If you ask for the information of that full message, taking this negative log expression, because logarithms turn multiplication into addition, this breaks up really nicely as the sum of the information for each individual letter. In the final part of this trilogy, I'm going to walk you through a very specific compression algorithm that would actually compress this text to within 1 or 2 bits of this value. It's no longer as simple as mapping each character to a predefined code word, but you nevertheless get this very direct sense of thinking about adding up the fractional information content of each letter to determine the length of the final encoding that you use. So that's the key idea. Even if, by the time you need to relate this to actual data sizes, things will get rounded off to the nearest whole number, what Shannon realized is just how useful it is to work at this higher layer of abstraction, where all your information is allowed to freely be continuous, and information of successive events really nicely adds together. Still, if you step back and imagine yourself very seriously assessing the fundamental compressibility of language, all of this hinges on the question of how you know the probabilities for each successive letter. Here, for all these animations, I've been illustrating things using a language model. But for one thing, that doesn't necessarily feel the same as the true probabilities underlying language. And for another, it's not even clear what we would mean by the true probabilities of language. So here, I actually think it's most enlightening to take a step back in time and see how Shannon himself thought about all of this long before language models or modern data analysis. Some of his earliest experiments on the information of language involved looking at specific short sequences of characters, what you often hear referred to as n-grams, and then tracking the statistics of what tended to follow. So, for example, if you scan through a few books and you notice every single time the two letters TH come up and you record what letters tend to follow, you could build up a table of those letters and let those statistics represent a sample for the probabilities you care about. Now, the problem is that this just completely breaks down for longer strings of letters, most notably any string of text that never shows up in all of the books that you're analyzing. Nevertheless, it's perfectly reasonable to talk about what's expected to follow such a longer string. In fact, if anything, it's more important to talk about those cases, since longer context windows are when things are at their most predictable, and that's where you stand to get the most compression due to that predictability. So instead of using raw statistics, a little bit later, Shannon analyzed a different model of the English language that he had available to him. His wife, Betty. As the story goes, Shannon pulled.
So I'm assuming that this guy basically started with some random string of letters and asked his wife to complete, like, just give him the next letter in the same sequence. And based on the probability of uh, this next letter appearing after this certain prefix, he started calculating the probabilities, and that's how he made his first model because it's not really feasible to go through all the English book, especially around the time when Shannon was born. When was Shannon born? Shannon Dick. Not this. Cloud Shannon. Oh, fun fact, Cloud Shannon is the person जिसके नाम पे Anthropic named their cloud. I forget. Oh, 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 his wife outlived him by 16 years. Information theory paper. Uh, Engram paper. हाँ, basically 1948 में this guy was doing all these discoveries. So there was no such OCR model, right? From which he could model ki, अच्छा हाँ, these are the probabilities of the next token appearing given a certain prefix has already appeared in the textbook. So he started using his wife. She might not be a perfect replacement, but she was pretty smart as we saw in that bio.
Pulled out a book and began asking Betty to guess each next letter. Shannon would then transcribe her guesses letter by letter. Every time she guessed incorrectly, he wrote down the correct letter, and then whenever she guessed correctly, he would just replace it with a dash. The idea was that this transcribed version he was creating has fewer actual letters than the original, but his point was that it contained the same amount of information, at least in the following sense. If he could somehow obtain an exact replica of his wife and conduct the guessing game again, he would only need to supply her with this reduced text. These letters, by themselves, would provide just the right prompting for his duplicate wife to exactly reproduce the original. Of course, in practice, a person wouldn't necessarily guess the same way twice, and while this qualitatively conveyed the idea of predictability allowing for compression, it wasn't yet a measurement of information. A bit later still, in his 1950 paper, Prediction and Entropy of Printed English, Shannon updated the experimental design to get a more robust read on this slippery question of the average information content in English. This time, interviewing more people, instead of just logging whether each guess was right or wrong, Shannon recorded how many guesses were necessary for a human guesser to come up with the correct next letter. And then separately, they had this whole method for associating the number of guesses required with an implicit probability that a person would have been assigning to the true next letter. Details of that are a little bit in the weeds, but the broader point I want to make is how, in analyzing language, he wasn't just doing pure data analysis looking through books. He was trying to probe at an underlying model of language, namely the interviewee's brain. These brains that he could talk to were effectively treated as black boxes, ones with a sophisticated and yet indescribable understanding of language and an ability to predict characters based on the context. Now, these days, in the 2020s, we've gone from merely interrogating black boxes that process language to designing them. The reason that you and I are here, revisiting the roots of information theory and this study of how compressible language is because of how much of the math in modern machine learning leverages the formulas that emerged in this field. Aside from the definition of information itself, there are three more key expressions that I want you to feel like you could have rediscovered, not just because rediscovery makes them more memorable, but because seeing how they naturally arise from studying compression gives a more and intelligence based on every. But imagine you have any provoking interplay between compression and intelligence. You already have everything you need to reinvent the first of these, which is entropy. Imagine you have any signal that can be thought of as a sequence of symbols, whether that's the 4 robot instructions, the English language, or really anything else you dream up. Entropy asks about the average amount of information for each symbol. And then based on everything we've been discussing, where perfect compression looks like random noise, and how, in that case, the number of bits used for a message is the same as the information content of that message, which again breaks down really nicely as the sum of the information of all the symbols. This question of measuring the average information per symbol is basically asking about the limit of compression. It would give you a lower bound on how efficiently a given signal could be compressed. And you and I already calculated this in one setting when we took that weighted sum to find the average bits per instruction for the perfect encoding of the robot case. Basically, because that encoding was perfect, each symbol's code word length is exactly the same as its information content. So effectively, we were calculating the average information per symbol. To generalize this, here's how that looks. For any given probability distribution, characterizing whatever symbols your messages are made out of, the average information per symbol should look like adding up p times the negative log of p for each probability p in that distribution. And take a moment to notice how we're visualizing this expression. Throughout the video, we've been picturing probability distributions with stacked horizontal bars, where each bar's width is equal to its probability, so altogether they add up to be 1. Now, above each one of those, I've put a rectangle whose height is locked to be the corresponding information value, the negative log base 2 of that probability. So the weighted sum up top, the average information per symbol, can be thought of as the total area of all these rectangles together. This is not yet fully general. It only describes the compression limit in cases where every new symbol follows some identical distribution. That's true in the robot case, but it's not true in English, for example. Nevertheless, it's important enough to deserve a name. And there's a fun story about how John von Neumann supposedly told tangles. To generalize this, here's how that effectively symbols perfect encoding of the robot case. Basically, because that encoding was perfect, each symbol's code word length is exactly the same as its information content. So effectively, we were calculating the average information per symbol. To generalize this, here's how that looks. For any given probability distribution, because would give you information per symbol is basically asking about the limit of compression. It would give you a lower bound on how efficiently a given signal could be compressed. And you and I already calculated this in one setting when we took that weighted sum to find the average bits per instruction for the perfect encoding of the robot case. Basically, because that encoding was perfect, each symbol's code word length is exactly the same as its information content. So effectively, we were calculating the average information per symbol. To generalize this, here's how that looks. For any given probability distribution, characterizing whatever's look in that distribution. And take a probability to its probability, so altogether they add up to be 1. Now, above each one of those, I've put a rectangle whose height is locked to be the corresponding information value, the negative log base 2 of that probability. So the weighted sum up top, the average information per symbol, can be thought of as the total area of all these rectangles together. This is not yet fully general. It only describes the important enough to percentage. I looked into both for the idea of entropy, about how John von Neumann supposedly told Shannon that he should call this expression entropy, since for one thing, it resembles an expression already used for the idea of entropy in statistical mechanics, and for another, quote, nobody knows what entropy really is, so in an argument, you'll always have the advantage. I looked into it, it's probably apocryphal, but there seems to be a grain of distribution, even maybe with one event dominating the probability space. This would have a very low entropy, since that one overwhelmingly probable event carries correspondingly little information. And then also, if you divide up the probability space even more, meaning it's distributed over more total possible symbols, each one has more information, so the total entropy is higher. And once more, it's fun to kind of slosh everything around, where a very skewed distribution gives lower total entropy, whereas a more even spread gives us higher entropy. The vague qualitative intuition here is that entropy measures the amount of uncertainty in a distribution. The more precise understanding, justifying why it deserves to be given in units of bits, is that it describes the minimum number of bits per symbol necessary to encode a message following this distribution. That statement and everything we just covered is more or less the content of a core theorem that distribution gives lower total entropy. Mask is more information theory, the noiseless coding theorem. It states that no encoding can ever be more efficient than this limit, and even more strongly, he showed that it's always possible to get arbitrarily close to this limit. Now, like I said, this expression only applies in cases where every symbol follows the same distribution, but Shannon was, of course, keenly interested in a more general setting, where the probabilities for each new symbol don't necessarily follow the same distribution. In particular, he spent a ton of time contemplating the compressibility of natural language. This requires a more general notion of entropy, something known as the entropy rate for a stochastic process, but it's the same basic question. What is the average information per symbol? Except in this case, we're now averaging over all possible messages. This is almost never a clean calculation that you can perform with some clean visual like the one we were just playing with. After all, what formula describes the probability distribution for language? So if you hear reference to the entropy of language, this is well beyond what any exact calculation can give you. Hence why Shannon turned to estimates based on observation. And again, his methodology was not just data analysis. It's not some function that you can perform on a corpus of text. In order to get a satisfying estimate on compressibility, he found himself inevitably needing to probe at intelligent models of language. When his interviewees had at least 100 preceding letters of context, he estimated the entropy of English to be about 1 bit per character. This is a pretty wild number when you think about it, because it suggests that English could be compressed down to just a single yes or no answer for each character. Wild as that sounds, in the third part here, I will show you that algorithm I've referenced, where if you're allowed to use a high-quality language model for encoding and decoding, you can get surprisingly close to this limit in practice. Before then, it helps to understand a variation on entropy, known as cross-entropy, asking both how and why it's used in training large language models. If you want to learn that, as well as a few fun related ideas like how large models are distilled into smaller ones, and why on earth gzip can recover the structure between distinct languages, come join me in part 2. How agents can explore aligned career opportunities. The meaningful update is just how there's a kind of wild paper from 2002 called Link.
Amazing. Oh, think this is enough for today. Let me set connection. You. Bye bye.